In this video, we are going to study about the historical background of electricity and magnetism, the role of electrostatic force in our daily life, Coulomb's law and superposition principle. In this chapter, electrostatics, we are going to study about the historical background of electricity and magnetism, the role of electrostatic force in our daily life, Coulomb's law and superposition principle, the concept of electric field, calculation of electric field for various charge configurations, electrostatic potential and electrostatic potential energy, electric dipole and dipole moments, electric field and electrostatic potential for a dipole, electric flux, Gauss law and its various applications, electrostatic properties of conductors and dielectrics, polarization, capacitors in series and parallel combinations, the effect of a dielectric in a capacitor, distribution of charges in conductors and corona discharge, and finally we are going to study about working of a Van de Graaff generator. Now, let us have an introduction about electrostatics. First of all, let us know what is electromagnetism. It is one of the most important branches of physics. The technological developments of the modern 21st century are primarily due to our understanding of electromagnetism. The forces we experience in our daily life are electromagnetic in nature, except gravity. And in a previous class, we have studied about the gravitational force, tension, friction, normal force, etc. Sir Isaac Newton treated them to be independent of each other, with each force being a separate natural force. But what will be the origin of all these forces? It is now understood that except gravity, all the forces which we experience in our daily life, like tension in a string, normal force from the surface, friction, etc., they all arise from electromagnetic forces within the atoms. Now let us see some examples. The first case, when an object is pushed, the atoms in our hand interact with the atoms in the object, and this interaction is basically electromagnetic in nature. When you stand on the Earth's surface, the gravitational force on us acts downwards and the normal force acts upward to counterbalance the gravitational force. So what is the origin of this normal force? This arises due to electromagnetic interaction of atoms on the surface of the Earth with the atoms present in the feet of the person. Though we are attracted by the gravitational force of the Earth, we stand on the Earth only because of the electromagnetic force of atoms. The third case is when an object is moved on a surface, static friction resists the motion of the object. This static friction arises due to electromagnetic interaction between the atoms present in the object and atoms on the surface. Kinetic friction also has similar origin. So from the examples given above, it is clear that understanding electromagnetism is very essential to understand the universe in a holistic manner. The basic principles of electromagnetism are dealt with in the first volume in this book. This unit deals with the behavior and other related phenomena of charges at rest. So this branch of electricity, which deals with stationary charges, is called electrostatics. So now you have the question, what is electrostatics? So for that you should write it as the branch of electricity which deals with stationary charges. That's called electrostatics. Now we will have the historical background of electric charges. The Greeks about 2 millennium ago noticed that amber, which is a solid translucent material formed from the resin of a fossilized tree, attracts small pieces of leaves and dust after rubbing with animal fur. The amber possessing this property is said to be charged. It was first thought that amber has this special property, only amber. But later people found that not only amber but even a glass rod rubbed with silk cloth attracts pieces of papers. So glass rod also becomes charged when rubbed with a suitable material. Now let us consider a charged rubber rod hanging from a thread, which is as shown in the figure 1.1. Suppose another charged rubber rod is brought near the first rubber rod, then the rods will repel each other. Next, if we bring a charged glass rod close to the charged rubber rod, they attract each other. And at the same time, if a charged glass rod is brought near another charged glass rod, both the rods will repel each other. So from the observations, let us have these inferences. The first one is the charging of rubber rod and that of glass rod are different from one another. The second one is the charged rubber rod repels another charged rubber rod, which implies that like charges repel each other. Similarly, we can also have the same inference by observing a charged glass rod repels another charged glass rod. The third case is when the charged rubber rod attracts the charged glass rod, implying that the charge in the glass rod is not the same kind of charge present in the rubber. So, unlike charges attract each other. Therefore, there are two kinds of charges existing in the universe. So, in the 18th century, Benjamin Franklin called one type of charge as positive and another type of charge as negative. So, based on Franklin's convention, rubber and amber rods are negatively charged while the glass rod is positively charged. Now, we have this following inference. That is, if the net charge is 0 in the object, it is said to be electrically neutral. So this is the diagram of attraction and repulsion between the glass rod and rubber rods, depending on the nature of charges present in them. So following the pioneering work of J.J. Thomson and Rutherford in the late 19th and in the beginning of 20th century, we understand that the atom is electrically neutral and is made up of negatively charged electrons, positively charged protons, and neutrons, which will have zero charge. Material objects made up of atoms are neutral in general. When an object is rubbed with another object, some amount of charge is transferred from one object to another due to friction between them, and the object is then said to be electrically charged. Charging the objects through rubbing is called triboelectric charging. Now we will see about the basic properties of charges. This is very important one. The first case, let us study about the electric charge. Most objects in the universe are made up of atoms, which in turn are made up of protons, neutrons, and electrons. These particles have mass, an inherent property of particles. Similarly, the electric charge is another intrinsic and fundamental property of particles. The nature of charges is understood through various experiments performed in the 19th and 20th century, and we will have the SI unit of charge, that is Coulomb. The second case is conservation of charges. Benjamin Franklin argued that when one object is rubbed with another object, charges get transferred from one to the other. Before rubbing, both objects are electrically neutral, and rubbing simply transfers the charges from one object to the other. For example, when a glass rod is rubbed against silk cloth, some negative charge are transferred from glass to silk. As a result, the glass rod is positively charged and silk cloth becomes negatively charged. From these observations, he concluded that charges are neither created nor destroyed but can only be transferred from one object to the other. This is called as conservation of total charges and is one of the fundamental conservation laws in physics. It is stated generally as The total electric charge in the universe is constant and charge can neither be created nor be destroyed. So in any physical process, the net change in charge will always be zero. And the third case is quantization of charges. What is the smallest amount of charge that can be found in nature? The experiments show that the charge on an electron is minus E and the charge on a proton is plus E. Here E denotes a fundamental unit of charge. The charge Q on any object is equal to an integral multiple of this fundamental unit of charge. Therefore, we will have Q equal to n times E. Where n is any integer 0, plus or minus 1, plus or minus 2, etc. This is called as quantization of electric charge. Robert Millikan in his famous experiment found that the value of E equal to 1.6 in 10 power minus 19 Coulomb. The charge of an electron is minus 1.6 in 10 power minus 19 Coulomb and the charge of a proton is plus 1.6 in 10 power minus 19 Coulomb. When a gas rod is rubbed with silk cloth, the number of charges transferred is usually very large, typically of the order of 10 power 10. So the charge quantization is not appreciable at the macroscopic level, since the charges are treated to be continuous, not discrete. But at the microscopic level, quantization of charge plays a vital role. And in this example, we are asked to calculate the number of electrons in 1 coulomb of negative charge, for which the solution is also given. Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of the 2-point charges and is inversely proportional to the square of the distance between the 2-point charges. Now we will study about Coulomb's law. This is for the electric charges. In the year 1786, Coulomb deduced the expression for the force between two stationary point charges in vacuum or free space. Consider 2-point charges Q1 and Q2 at rest in vacuum and separated by a distance of r, as shown in diagram 1.2. According to Coulomb, the force on the point charge Q2 exerted by another point charge Q1 is given by the equation 1.2, that is F21 equal to K times Q1 Q2 by R square into R12 unit vector. This R12 unit vector is a unit vector directed from charge Q1 to charge Q2 and K is a proportionality constant. In this diagram, the Coulomb force between two positive point charges is given. Now let us see about important aspects of Coulomb's law. First one, Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of the 2-point charges and it is inversely proportional to the square of the distance between the 2-point charges. The second one is the force on the charge Q2 exerted by the charge Q1 always lies along the line which joins the two charges. And R12 cap is the unit vector pointing from charge Q1 to Q2. It is shown in the diagram 1.2. Likewise, the force on the charge Q1 exerted by Q2 is along minus R12 unit vector, that is in the direction opposite to that of R12 unit vector. The third case, in SI units, K equal to 1 by 4 pi epsilon naught and this value is given by 9 in 10 power 9 nm square T power minus 2. Here epsilon naught is the permittivity of free space or vacuum and this value is given by epsilon naught equal to 8.85 in 10 power minus 12 C square n power minus 1 m power minus 2. The fourth case is the magnitude of electrostatic force between two charges each of 1 coulomb and separated by a distance of 1 meter is calculated as follows. So F is equal to 9 10 power 9 into 1 by 1 square, that is given by 9 10 power 9 Newton. This is a very huge quantity, almost equal to the weight of 1 million ton. We never come across 1 coulomb of charge in practice. Most of the electrical phenomena in day-to-day life involve electrical charges of the order of microcoulomb or nanocoulomb. In fifth case, in SI units, Coulomb's law in vacuum takes the form F21 vector equal to 1 by 4 pi epsilon Q1 Q2 by R square R12 vector, unit vector. In a medium of permittivity epsilon, the force between 2-point charges is given by F21 equal to 1 by 4 pi epsilon Q1 Q2 by R square R12 unit vector. Since epsilon is greater than epsilon naught, the force between 2-point charges in a medium other than vacuum is always less than that in a vacuum. We define the relative permittivity for a given medium as epsilon r equal to epsilon by epsilon naught. For vacuum or air, epsilon r equal to 1, and for all other media, this relative permittivity is greater than 1. In the sixth case, Coulomb's law has some structure as units of gravitation. Both are inversely proportional to the square of the distance between the particles. The electrostatic force is directly proportional to the product of the magnitude of 2 point charges, and gravitational force is directly proportional to the product of 2 masses. But there are some important differences between these two laws. The gravitational force between two masses is always attractive, but Coulomb force between two charges can be attractive or repulsive, depending on the nature of charges. The value of the gravitational constant G is equal to 6.67 in 10 power minus 11 nm square kg power minus 2. The value of the constant K in Coulomb's law is K equal to 9 in 10 power 9 nm square kg power minus 2. Since K is much more greater than G, the electrostatic force is always greater in magnitude than gravitational force for smaller size objects. The gravitational force between two masses is independent of the medium. For example, if 1 kilogram of two masses are kept in air or inside water, the gravitational force between two masses remains the same. But the electrostatic force between the two charges depends on the nature of the medium also, in which the two charges are kept at rest. Next is 7th one. The force on a charge Q1 exerted by a point charge Q2 is given by 412 equal to 1 by 4 pi epsilon naught Q1 Q2 by R square R2 1 unit vector. Here R2 1 unit vector is a unit vector from charge Q2 to Q1, but R2 1 unit vector is equal to minus R1 2 unit vector. So F12 is equal to minus F21. Therefore, the electrostatic force obeys Newton's third law. Next one is 8th one. The expression for Coulomb force is true only for point charges, but the point charge is an ideal concept. However, we can apply Coulomb's law for two charged objects whose sizes are very much smaller than the distance between them. In fact, Coulomb discovered its law by considering the charged spheres in the torsion balance as point charges. The distance between the two charged spheres is much greater than the radii of the spheres. There are few example problems given here with the solutions, and you can practice them well. Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of the 2 point charges and is inversely proportional to the square of the distance between the 2 point charges.